So one thing I'm going to give you, and we're going to get a lot more examples of the Faraday's law today. That's all we're going to primarily do, just qualitative stuff. I want you to have a little bit more time on the homework, so I'm going to give you an extra day on the homework. So meaning it will be due on Friday. So homework 9. Okay. Homework 9 due Friday. And then when's our exam? The 28th. It's on Monday. Okay. So test 3. Monday. In lab. April 20. Also, I should mention that since I'll be in Vancouver, I have to look for Vancouver on the 3rd of that one class. We will not have class May 5th. So there is a class on May 5th. That's when the semester ends. I'll be in Vancouver and it'd be hard to give the lecture. So no class. May 5th. And I'm planning on having the final the same day as it should be. Just make sure there's a proctor, somebody that you can talk to. I've talked to my colleagues about having somebody who can help you out if you have any questions on stuff like that as well. Nothing is going to be, obviously I can't grade things until I get back. The claim is whatever this means. Person putting it together claims are going to be back. The 9th. I don't know if that means early in the morning or at night. I honestly don't know what that means. So the earliest I can get to your exams is probably most likely the 10th. Are we coming back on the 10th? We might be coming back on the 10th. So the earliest I can get things is going to be on the 11th. And so I won't have anything graded until minimum of the 12th. So just so you know how things are scheduled there. Okay, so let's do more examples of Faraday's law. And Lenz's law. So we have this right here. This is Faraday's law. And what did we say this side over here is? And it looks like a voltage, but it's not a voltage. It is a EMF. And EMF stands for a electromotive force. And so why isn't it a voltage? What's special about that? Let's see. In the delta V expressions, the electric field was always a what kind of field? Conservative. This is actually a non-conservative. And that's actually why it's not a true voltage here. And it has to be a conservative, if it's a conservative electric field, then that's would be a true voltage. And then in which case, if you loop all around the whole thing, you get a 0. Now, where is Lenz's law of this? Is that Lenz's law is the minus sign here. This is Lenz's law. And it's not really a minus, it is a minus sign, but it's not really a minus sign, it's kind of a fake sign. What does it mean? It means that the induced current will be set up in such a way as to I want another word in review. You don't have. As to oppose the change in magnetic flux. So it's always going to, whatever the change is, it's always going to try to oppose it. And then again, for those who just came in, the homework is not going to be due on Friday. Just because I want you to have a little more time to kind of think about it. If you're just going to take examples. And then on May 5th, that last day of classes, there will be no classes because I'll be in Vancouver.
When's it final?
Whatever's on the syllabus, we're going to keep the same date.
It's just like a Saturday at 10.
This Saturday at 10.
What's with the syllabus?
There's a chance I'm not exactly. I do not know. Again, I have to check when I'm coming back. So about the time change and stuff like that. I haven't said idea. We're flying out of Toronto because there's like 8 of us going. This connection with the engineering department. And it was cheaper for us to fly en masse out of Toronto. So Go after the back. We're making arrangements, I'm not. So all we're gonna do is a minus sign stuff today. Let's try this one. So let's say I have, what would that device be called? That'd be called a solenoid, right? Now I'm gonna have another one over here. The question is, when I throw that switch, what's the direction of the induced current over here? So when the switch was thrown, what is the direction of the induced current on the right solenoid? You're going to throw that. The question is, what's the direction of the induced current here? And why? First of all, let's ask the question. What is the magnetic flux when the switch is open here? What's the magnetic flux going through the solenoid? Zero, right? There's nothing in there to produce a flux. Okay, now we throw this switch. If I throw that switch there, what's the direction of the current here? If this is positive, the current goes this way. Hey, what's the magnetic field then for our little solenoid from that? How do we run that? How does this right-hand rule go? You take your fingers. Yeah, the wire is wrapping like this, so wrap your fingers in the direction that the current's going around the solenoid, and your thumb points in the direction of B. So that's what we have here. Okay. So now what's going to be the direction of the flux now going through here because of this? Initially it was zero, now it's what? Now it's increasing in this direction. Does that make sense? So here, the flux, magnetic flux through the right solenoid is increasing in the direction. Okay. What does Lenz's law state? This right here wants to oppose the change. So how does this oppose that? If this is saying a magnetic field, a magnetic flux increasing this way, how does this then oppose the changing and increasing flux this way?
Well, it's going the opposite direction.
The magnetic field is going to have to go in the opposite direction. So this one over here has to create an induced field this way. This right here, this is the induced B field. Opposing the increasing flux. In the direction. Okay, so how's the current have to go? Use your right hand rule in reverse to figure out the direction of this guy here. So you point your thumb down in the direction of the magnetic field, and your fingers wrap in the direction of the current. The current has to go. Now, let's look at this over here. And this part over here, is this acting like a south pole or a north pole on this side? Because the field lines are going in. But now over here, what is this going to act as? This acts as the south. What do south poles do? They repel. And you can see that again, that's again, the reason why this is happening is the conservation of energy. If this were a north pole, what would happen? This would start moving this way like that. And actually, then you'd be violating conservation of energy. Okay. Now. There's a tricky question. That was part A. Part B of this same question is. If the switch remains closed. What is the direction of the induced current? In the right solenoid. So we throw the switch, as soon as we throw the switch, we get this, that's our induced current, induced B field. But now we leave the switch thrown. What's this gonna be now? Okay, what's the change? If this switch remains shut, how does this magnetic field here change?
Yes, stronger.
Can't wait to find out. If it's thrown like this, the current stays I. The current stays I, what can you say about the magnetic field? Stays the same. So this magnetic field stays the same. How's the changing flux going through here? It's not changing. So what's going to be the increased current? 0. What happens here is that since the flux, since the magnetic flux from left solenoid is no longer changing. The induced current will be 0. You throw the switch, you immediately get this, then it dies away. Hey, what do you think part C of this same question is going to be? What are you going to do to that crazy switch? Let's pop it open. The question is, actually, I shouldn't go do this over here. Part C. If the switch is opened, what is the direction of the induced current? Okay. So let's draw that a little picture here. I'm just going to draw the exact same picture, it's just one a little. The speed field light. Okay, so what's the original direction of the flux through here? When that switch is shut. This thing is going to have some flux going through it like this from this field here. So the flux through the right solenoid from the left solenoid. This is right. Initially. Yeah. If we open up that switch, the switch is open. What happens to this magnetic field here? Yeah, there's going to be no current, so that magnetic field, that flux has to be 0. So what's gonna be the change in the flux over here? Flux is initially going this way. Now what's happening to it?
Goes to the right.
Okay, it's actually gonna decrease this way, because right, when we open this up, this magnetic field going through here, so the change, and again, you have to look at the change. The change in flux is decreasing in this direction. And so if the switch is open, flux in the direction on, let's say, for the right solenoid decreases. And so now you have to oppose the change. So the change is that the flux going this way is getting weaker. The flux getting this way is getting weaker. How do you oppose the change?
Increase the flux in the direction.
You have to increase the flux in that same direction to bring it back up to what it used to be. And has to happen over here. That this, when it creates a B field here, has to go in the same direction. And you bring it back up to what it was. So the flux in the right solenoid is to the, okay, to decrease, to oppose the decreasing flux. In the direction. So how's the current have to go then? Up, down, right, left. And you point your thumb in the direction of the B, and your fingers go like this. Goes like that. So if you took the switch and went basically open it up and back like this, what would happen to the current over here? Yeah, it's going to keep on flipping like that. Again, you can already see how you're starting to make AC current actually occur in a very natural fashion. Okay. Questions? Now the cells were removed. Really, okay, that's faster than I wanted to. All right, let's look at the kind of the setup we had the other time. We played with that, so you've probably seen it. So let's look at the setup here. So this is a pole face of a magnet. Let's say it's going to do this. Remember what we had here. So we had that magnet here, and then we had that metal square that could actually oscillate like this on pendulum. So we had it over here. This came down here like this. Okay, this was aluminum metal. This is aluminum. This is a pivot. And what happened when it came into the field, it stopped almost immediately. That's an example of what's called magnetic braking. So let's figure out why this is occurring. So when this comes down here like this, and it's like this. Okay, it's swinging this way. Okay. What's happening to the flux through that metal? Remember what your magnetic flux is. Your magnetic flux is this. This is through a loop. Okay. So the B is not changing, but what is changing? If I just say calculate the flux through this little region here, what would happen? What would be the flux out in this region here? Zero, because there's no magnetic field. So all the flux would be here, right? So as this swings in here, it's not the B that's changing. What's happening? The area that the B is going through is changing. This is why the flux is changing. Now, is that flux increasing or decreasing, and also in what direction? It's going to increase. Okay, so it's increasing the further it goes in here. In what direction if the B field's like this? Into the board. So as the sheet of metal moves into the moves between hole faces, the flux here increases into the page. Okay, so now how does this oppose it? If this wants to oppose the changing flux, the flux is increasing this way. So how can it oppose? How can that sheet of metal oppose the increasing flux? It has to create its own B field coming out. So this is going to have to create its own B field coming out like this. So this right here, this is the induced B field. Of the metal sheet. Opposing the increasing by the into the board. Now here's the tricky part. To figure out here. So how does that current then have to go? That you're going to actually have some current induced in that metal sheet. And how that current have to go? You take your thumb, you point it in the direction of that induced B, and your fingers wrap like this. So what are you going to have to do? You're going to have to get induced currents like this in the metal. So these currents that you're inducing in the metal are called eddy currents. So to produce the induced current, so the induced B field, induced currents are set up like off to the phantom zone. Not yet. Are set up in the metal. In the metal sheet. Okay, so these induced currents, these currents are called eddy currents. These induced currents are called eddy currents. Now, what do you know about if you have a current going through a magnetic field? Does anything happen to a current going through a magnetic field? Yes. What happens? There's a force on it. And what do we know about that force? It's given by F equals. Oh, that'd be for the point charge. When you go to the wire, it's given by I. The wire here is I L cross B. Yes. So this part over here on the current, what's the magnetic field out here?
Yeah.
0. So there's no force on this part. No force here. Now tell me about on this side here. What's the direction of the force on that one there due to that external B field? I was going this way, so your fingers point in that direction. Exactly. So this right here, if you do the IL cross B here. That's going to be a force on this one going that way. So what happens to that as it goes in? There's a force going this way here, and it causes that whole thing to stop. That's your damping force. Okay, that's how magnetic braking works.
Is it effective?
No, it's very effective. You saw it when we did the pendulum thing, how it just immediately stopped the thing.
Where's the L?
The L here, I mean, it's not, doesn't work out perfectly because this L would be kind of like the snake along here like this. but it's the same idea. And so, you know, when we put that in there, it stopped really quite fast. Now, what could you do with this? Okay, at some point you go on these rides, what do they do? You hop in a chair. So there's a big tower like this. You hop in here. These are all the people in the ride, and they move you up to here. And what do they do once you get up there? They'll let you drop. Okay, now presumably you don't go here and smash into the ground and everyone dies. It turns out that ride never caught on. So what do you want to do? You want to break the people. I mean in the sense of slow them down. Now you could have brakes on there, and they do, but what else could you have on here? Okay, I don't honestly know if they have this, but I think they probably have to. Because I would want to make certain that no matter what, I want to have something that's independent of the mechanical properties. And so what could I do? I could have actually a big metal fin down here. It's connected actually to the seat. And then I could have magnets like this. So as that comes down here, there's going to be a force up like that, and that'll then stop you from actually, smashing into the ground like that. It's independent of any type of mechanical braking system or it's just fixed in there. You can also do something else. Let's say you can have a table like this. So here's the table. And sometimes you have some experiments up here. So there's some sort of experimental setup. And sometimes those experimental setups are so fussy, what you don't want to have happen to that table. You don't want it to move at all. You want basically all the vibrations in that table to basically not exist at all. So if you go like that, you want those vibrations to stop immediately. So what can you do? Well, first of all, these tables are ridiculously expensive. There's often a lot of optics experiments, very, very, very elaborate microscopes on here, things like this. So what you can do, first of all, you have like cushions of air in here, but also you can have basically metal plates in here like this, with fields like this. A metal plate, fields like this, and all the legs here like this. So what's going to happen here is that if you move this, if that jostles anyways, you're going to induce eddy currents here, and it's going to dampen all the vibrations. And it's very effective. Now you can screw it up, because this actually happened to me, and as I've survived this. So when I was a grad student, I wanted to go have lunch with my friends. So they were doing an experiment. It was like just a little bit before noon. So I had it on my backpack, and they were doing something, and I didn't pay attention. And there was a table. I took my backpack and I slung it on the table. I went, hey, let's have lunch. And it was one of these vibrational tables. And it basically set off all there's, as I said, there's air cushions in there and everything. And it set off all of them. Made a huge noise, and then all the vibrations stopped. And then my friends looked at each other, and then they looked at me. And then there were certain hand gestures that I received, and various names, which all involved 4 letters. And I had lunch by myself that day. Okay, and I deserved every single hand gesture and little comment that was made my way. Okay, so they're effective. They're effective. I just don't recommend dropping a book bag on a backpack and people are doing something experiment. Not designed for insanity. But they're effective. That makes sense? Let's try another one. So let's say this is a region of constant V. Here and here. So the B is only in that region. What I'm going to do is I'm going to take a metal loop. So here's a metal loop. I'm going to pull it this way. That's me pulling. And I'm going to have it here. This is going to be part A. This is point B. This is point C. I want you to find the direction of the induced current in each of these. Find direction of induced B. well, let's say induced current. In each case. So as we start, first of all, moving that loop into that field, what's going to be the direction of the induced current? Up, down, right, left, clockwise, counterclockwise. Spiral. Counterclockwise. Does Raleigh get thumbs up? It's down. Oh, the magnetic field's going that way then. I think she gets thumbs up. How come? And always ask yourself, what's happening to the flux? Is it increasing or decreasing? So the flux is going into the board because the B field's going into the board. If you grab that loop and continue to move it further and further in, what's happening with the what's happening to the flux? Is it increasing or decreasing into the board? It's increasing into the board. So if this is actually seeing something increase into the board, how does this work? It has to create its own B field coming out of the board. So this one here. So the induced B has to be like this. This is the induced B. So how's the field have to go then? Thumb in the direction of the induced B. Fingers wrap like this. That would be this right here. And your I induced. Now, if this is me, if I'm grabbing this here and pulling it like that, am I going to feel any resistance on this? Yes. And where's it going to come from? Okay, we have current this way going up. And I have a field from the external field going into the board. What do I know about this? If I were to apply F equals this I induced here. L crossing basically our V external. Okay, what happens here? What would be the direction then on this side here? I crossing the B, that force is this way here. What would be the direction of the force on this side? What's the B out here? 0, so there's no force. What about the forces on these two sides here? On the top, it would be going. I is this way on the top. B's into the board. L crossing the B. Down. What about on this side? So they're going to cancel. So, but you're going to feel actually resistance, actually trying to pull it in there. And you saw that. Remember when we took that metal plate and you put it in there in the field, you could actually feel that. You could feel actually very strong resistance resistant force. Okay, what about here? And it's all in the interior. The flux is going into the board. And how's it changing as you're moving it while it's still in the interior? How's the flux changing? It's not. So if there's no changing flux, again, remember Faraday's law. Your flux has to change with time. If there's no change in time, if the flux is not changing with time, this is 0. If this is 0, then there's going to be no induced current. So here inside, at this point here, there's no change. The magnetic flux, so I induced. That's 0. Okay. Now what happens over here? As we pull it out like this, the flux from the field is still going into the board. Now what's happening to it? Is that flux increasing or decreasing? It's decreasing. And it's decreasing into the board. So how can this thing oppose the decreasing flux into the board? It's going to create its own B field going in the same direction to bring it back up to what it used to be. So this has to be, this right here is going to be induced. And so what has to be in the direction of that current? Induced current. Point your thumb in the direction here. The fingers in the wrap in the direction of the current. Let you have this guy here. What's going to be the direction of the force on this guy? So in other words, if I try to pull this out of the field, Okay, your current's this way. B, your external force, your external field is into the board. L crossing the B, there's gonna be a force this way. What about on this one over here? Because. We've got magnetic field. That makes sense? Let's try another one. Let's say the current in here is given by I, let's say it's given by 4 e to the minus 3. And here's a loop. I want you to find the direction this loop moves in. And we're neglecting gravity and all this other stuff. I'll find the direction. Loop moves. A lot going on this problem. First of all, what's the direction of the current? I mean, okay, it's going this way. So what's the direction of the magnetic field? Okay, you point you grab hold of the wire, pointing your thumb in the direction of the current. Your fingers wrap in the direction of B. So down here, the B field is. Does that make sense? It's going like this, so it's going like this. So down here, it's going one way. Now, is that so? The magnetic flux going through this is going in. Now, is that magnetic flux increasing or is it decreasing? If this is my current. Okay. Is what do you know about this current here? It's the decaying exponential. What happens with the decaying exponential? It decays, right? The current goes it's an exponential decay. So this current's getting weaker. And what do you know about the magnetic field for a wire? This is one of these expressions you want to have completely hardwired into your brain. It's mu naught I over 2 pi r. So if the current gets weaker, the B field gets weaker. So what's happening to the flux going through here? So it's going to be decreasing this way. So how does this thing have to oppose it? So the flux, the phi B from the wire decreases with time into the board. And again, the reason it decreases is because I said you have a exponentially decaying current. Okay, how does this thing have to fight it then? Lenz's law states you want to oppose the change. So how do you oppose the change if it's getting weaker in that way? Yeah, you have to basically have something going in the same direction to bring it back up to what it used to be. So this is going to be our B induced. So how's that current have to go? How's this right here will go? Take your thumb and point it in the direction of the induced current. I mean, your induced B field. Your fingers wrap in the direction of the current. This is your I induced. Okay. We're almost done. Now we have to figure out which way this thing moves. So why would that thing even move? It has a current in a magnetic field, external magnetic field. So I'm going to do the IL cross B here again. So let's look at the force on each of these sides here. So the force on the top side, the I is this way, which means L is that way. The B induced, we're doing the external field. The external field is into the board. So that's a direction on the side here. L cross B, the side on the side is up. Let's give these names. This will be 1, this will be side 2, side 3, side 4. What about my friend on side 2? What about my third friend on the bottom? I cross B, this is down. What about on this side here? So which way does it move in Y? Toward the wire. I don't know. I'm using this for all the sides. Well, what is this causing? Where's my B external coming from? The wire. How does this side and this side differ? The R is your distance from the wire. So here's the R for this side. That's your R1 here. This is your R for this side, this R3. And the magnetic field on this side is weaker because it's further away. This one is stronger. The I induced is the same, the lengths are the same. But this force here is going to be greater than this one here. This is greater than the magnitude of the force 3. So there's going to be a net force going this way. This will be the direction of motion. What about on these sides here? What about 2 and 4? But that's what the B fields change. But your answer is correct.
Like the exact same length with the line.
Exactly. You could do, if you do point by point, the B fields change, but what's going to happen? The B here is the same, the B here is the same, right? It gets weaker as we go along here, but the change in it is going to be the same on each of these sides here. So bit by bit, they'll always cancel. That makes sense? Kind of cool. Now, let's see how an EMP weapon works. Okay, so. And first of all, what does it stand for? Yeah, this is electromagnetic fault. Okay. The name actually already implies what it is. So let's say here I have here's an electric circuit. Right. So I have all these transistors and everything. So I'll draw a little transistor here. Let's say I have a little resistor. I'll have another going to, let's say, another little capacitor, another one. So here are little transistors in my little circuit. Really, really complicated. Who knows what it is? Doesn't matter. Now, what would happen if I had a magnetic field like this? Okay, and this is changing. So this is an external B field. External B field, which changes in time. So the electromagnetic pulse, so I'm going to have some sort of pulse of, let's say, a magnetic field, okay, which is actually going to be changing with time. What's that going to do into my little circuit? Lenz's law is still operational. It's always true. So let's say this B field is increasing in this direction here. What is this going to do? Yeah, if this is increasing this way, this is going to actually induce its own B field in this direction here. That's going to be the induced B field. Hey, what's going to happen? You have to have an induced current, which the circuit is not designed for. Okay, so you get this induced current going like this to basically go like that. And what's that induced current going to do for the rest of the circuit there? Pretty much fry it. Okay, that's how those things work. It's really a Lenz's law device. How'd you make an electromagnetic pulse? Let's see how many James Bond fans we have here. When I was in grad school, GoldenEye came out. My friend kind of dragged me from and said, look, we're going to go see James Bond. It was very odd. It was actually a matinee. It was the first time it came out. It was the very first matinee. And the theater held like 400 seats like that. And it was all filled with guys. Just a very odd experience. There may have been like 1 or 2 women in the entire thing. It's all guys. Imagine that in a James Bond film. Who would have thought it? Anyways, the whole basis for that is basically they have an electromagnetic pulse weapon. Okay, and how do they use that? It's basically nuclear weapons. You basically detonate your nuclear weapon that produces an electromagnetic pulse from basically you have all these charged particles going up from the explosion. And then they induce basically, you're gonna take out your electronics like this. That's all basis for. Okay. Now. I mentioned before that actually nature produces its own version of this, and they're basically called solar flares. So. Here is our, let's draw. This will be Canada. Turns out Canada looks exactly like this. Okay. And here's the power grid for Canada. There's the power plant. Here's somebody's house. Okay. And what happens here, you basically have power going to the house and then power going back. So if you do a top view of this, what is this here? It's really, that's your power plant, wire going here, here's your house, which only has one resistor in it, okay, which goes back like this. This is basically what any power grid looks like, kind of simplistic level. Basically, any power grid, no matter what, is basically just a whole series of closed circuits like this. Okay, around the Earth, so the Earth also has a magnetic field. So there's some magnetic field here that's just normally here. So this is the gate here. Okay. So let's say this is going out, this is going. Normally what happens to the magnetic field of the Earth? Not a whole lot. So what's happening here? The flux from the magnetic field of the Earth is not changing with time. Fine. But let's say you now have a solar flare. Here's the sun. Here's the Earth. You have a view field like this. Now, you basically have solar flares, which are what? Charged particles. Basically protons and electrons. They're going to come, and we mentioned before that they basically circle around here like this, like that. And you can actually go through, NASA has a couple animations of this, or not just NASA, I think other people. When these solar winds actually hit the Earth here, actually it takes the magnetic field to the Earth and it actually flexes it. It's actually really amazing. Now, how that happens is that's not really understood. So when that field hits it, those fields actually change with time, actually quite dramatically. So what's going to happen? Those solar flares hit, and then these B fields, they can change like this. But they're changing like this. What's happening? The flux through here is changing. The flux through here is changing. What's going to happen to your little circuit? The current is going. You're going to have to get an induced B field in the circuit, which means you have to have an induced current. So you're going to get an induced current in the circuit here, which was not, the circuit was not designed for that. What happens when it took up the Canadian power grid? This was, I think, like earlier mid-90s, and it was, I think, almost the entire east coast of Canada was taken out. So some very, very large geographic region. It's entirely basically was nature's own version of an EMP weapon. So kind of cool. Okay. How does an induction stove work? You have a little oven top. You have your little metal pan on it. What's in an induction oven? The burners are going to be basically alternating magnetic fields. You put your little metal pan on it. If you have an alternating magnetic field in the top of your stovetop here, what's it going to do to the metal then? That magnetic field is changing with time. It has to, right? Lenses all still operable. So basically that metal is going to try to oppose the magnetic field changing. So it's going to induce a current in the metal pot, eddy currents. And those eddy currents are what it was heating up your metal pan. That's how an induction stovetop. That's Faraday's law. Okay. So that said, I think you can pretty much do all those little examples of on the homework, which is now due on Friday. So what we'll start tomorrow is I want to start looking at this analytically. How you do that. Okay, have a good day.
Mm.